So good morning, everyone. Again, my name is Tom Henderson. I'm with the University of Washington, and I'm here to start today's day-long discussion of some of the sidelink modeling in NS3. Thank you for attending. I'd like to first introduce, although she won't be presenting, we have one of the co-authors of the code that I'll be talking about, Samantha Gamboa here from NIST. Who's responsible for portions of this, and I'll point it out when we get to that point in the talk. And so let me get this wireless remote to work. Yeah, okay. All right, so today's outline is looks like the following. So we're going to have an early introduction this morning about some of the recent updates to the V2X branch of code that's on the CTTC GitLab site. And we're going to look at a couple examples and how it's demonstrating the capabilities of the additions to the sidelink code recently. And then following our coffee break, we'll have another tutorial by Lou Cowell, who's here, and Colin Brady, who's online, talking about a more research-oriented exploration into some of the resource allocation issues around sidelink and some of the validation of NS3 models against analytical models in that space. And then this afternoon, early on, we'll be having a tutorial from Samantha and Aziza from NIST, or working on the NIST project, to talk about proximity services sitting on top of the sidelink models, specifically discovery models and layer 3 UE to network relay models. And then finally, we'll have a panel discussion in the last session this afternoon on sidelink. So I'd just like to start by introducing some terminology because often people, in talking about this technology, bandy about the following acronyms: V2X, ProSay, SL for sidelink. Are these all interchangeable terms? So from my perspective and my understanding of it, V2X is an acronym referring to the use case that's enabled by an underlying sidelink air interface. And ProSay, proximity services, is another type of vertical sitting on top of the sidelink. And we'll hear a little bit more about that this afternoon. Sidelink itself refers to communications between UEs that do not go through the network. They can be, as I'll mention in a forthcoming slide, it can have some control elements in the network, or it can be completely autonomous. And not all of the sidelink use cases are involving vehicles. So V2X is probably one of the major drivers of it commercially right now, but there are other applications such as public safety. The NR-V2X modes, there's two modes that are defined in the standards. Mode 1 is where resource allocation is coordinated over the sidelink. Resource allocation on the sidelink channel is coordinated and managed by the network. And this is analogous to the predecessor LTE. I think this is a typo. This is mode 3. And then mode 2 is what we'll be talking about today, where the resource allocation is actually performed without any network assistance. And this is analogous to V2X mode 4. And so just before I get into the meat of this, I'd like to just acknowledge all of the people's work that built up to this point. This tutorial extends an introductory V2X tutorial that was given last year at our annual meeting by Zarez Ali. And if you go online to WNS3 2022 and look under the tutorial sections, you can see a video and slides from last year's V2X talk. I'll be talking about a little bit different topics than what was the focus last year. CTTC and Zarez are the primary authors of the V2X sidelink models that you see in NS3 today. Meanwhile, I've been working on a project that's been led by NIST, and a number of people at the University of Washington have worked on this, as well as people associated with NIST, on improving and extending these V2X models with an eye towards public safety applications and proximity services on top of that. And so finally, I'd just like to thank both CTTC and NIST for agreeing to open source the V2X sidelink and ProSe models for NS3. So there was a paper that's referenced in this talk by Zares, where there was a comparison between what's available on the V2X standard on the left and the features that are available in NS3. And what's new this year is you'll see from last year that there were a number of, let me move this a bit out of the way, a number of capabilities in black here in the right column. And we've added a number of new capabilities in red, which I'll be talking about today, principally the ability to send both groupcast and unicast communications instead of just broadcast, and the various harq models that support that, as well as a PSFCH feedback channel, and then some additional enhancements to the sensing and scheduling algorithms to support all of this work. Unreliable slide advancer here. Let's see. Oh, there we go. So just to introduce a little bit about how this code is structured. NS3 has moved to a modular code base, and we're no longer merging all of our models into the source directory in the main repository, but instead we're enhancing it with third-party or additional models that we install into what's called a contrib directory. And I think NR is probably the most prominent example of this. So when you build NS3, you will see a lot of these legacy models or pre-existing models built in the source directory. But if you recurse then into a contrib directory, it's normally empty by default when you install NS3. But through our app store or just downloading things through GitHub or GitLab, you can populate this directory. And the new radio models are probably the most prominent example of that. And so the public NR module is available on gitlab.com. It's CTTC's website. I've put the address here. And so there's a mainline new radio model, and then there are extensions for V2X. And these are in a separate branch on that repository. We also have NS3 extensions maintained and advertised or publicized on our app store. So if you go to the NR app, you'll see a page for it as well with instructions on how to download it and who to contact if you want more information. So I'm going to talk a little bit about putting all of this code together. NS3 and NR modules have to be paired with the appropriate releases. So what has gone on to date is that as NS3 has made a release, and we're about to make NS339 very shortly, there's been a corresponding new radio release that lines up with that, is compatible with it. And the NR module, if you just download it without the V2X extensions, doesn't require any patching of NS3. It's completely standalone from the rest of the NS3 code base. V2X is a little bit different. These extensions are not maintained in the master branch, but they're stored in a separate V2X, NR V2X dev branch. And they also require a special patched version of NS3 because they make some extensions into the LTE directory. So the upper layers of the V2X stack presently are leveraging code that's in the LTE directory, and some extensions were made there to support sidelink. So this special version of NS3 is also maintained in another CTTC repository and branch. And so I've put the URL here, and as a result, it's also lagging NS3 dev. And so these are kind of early releases that have been made, and you'll notice that they're against earlier versions of NS3. So this is the most recent snapshot release of this. But for our NS337 and 338, we don't have a corresponding release of V2X. Hopefully for NS339, we'll be able to advance that and have one matching, hopefully with some of the extensions I'm talking about this morning. And just for future reference, these are instructions to clone. I don't know how to get rid of, hide this menu bar. I'll work on that in a second. Instructions to clone the code from CTTC, and check out both this directory of special branch of NS3, and then recurse into the clone and recurse into the NR directory and check out a special branch there. So presently, if you pair up NR v2x dev with v2x LTE dev in the NS3 level, then these will be compatible. Any questions so far? Or questions from the audience? Does anyone know how to get rid of this Zoom ribbon on top? Maybe I can just move it down here. Is that better? Okay. All right. Yes, question. So the question is, could I relate the NS3 versions to the 3GPP versions? I would say that, so I can't on the spot directly answer that question, but because I think it's a mix. I don't know whether, Samantha, if you're familiar with which version that we've been focused on. Mm-hmm.
Then yeah, and basically we are taking everything else from LTE as well. So there is
yes. So yeah, so mainly release 16, some aspects of ProSay release 17, but then they leverage pieces that date all the way back to maybe release 12, 10 to 12 on the LTE side, especially in the upper layers. And so there's a lot more current models or current standards if you go into the Mac, lower Mac, than if you're looking at, for instance, PDCP, RLC layer or RRC layers, for instance. But it's a mix, and I would say that in my experience, there's not a single standard that says, okay, uniformly in this stack, we're all aligned with a particular release. It's been, pieces have been developed against different versions of the standard over time. Okay. So today's tutorials are actually using 3 customizations of these V2X branches. And what I'm going to be talking about this morning is on a branch on my personal fork of both NS3 dev and the NR module. And I've listed here the branch name. So if you check out these 2 branches, then you'll be able to reproduce the code that I'm talking about today. And these have gone through an introductory review with CTTC, with Zeraze. And I think the consensus is that once some documentations and further tests are written, these will be ready for merging upstream, and then potentially we could make a new release based on this. So this is something that we're hoping will occur over the summer timeframe. But in the meantime, you can pull off of this these 2 branches. There's a separate branch that Colin at UW has been working on, and he'll talk about that a little bit later. But I think it's pretty close to what's publicly available. And then the ProSay tutorials using another special branch that's available at NIST's GitHub repository. And that's because a lot of the public safety extensions that we've been working on over the years through the NIST funding are actually hosted on a GitHub site. And again, they also require some modifications to NS3 that are not in the CTTC site. So what I showed you earlier with the instructions on how to obtain this code, we see here that if you basically go to very similar instructions, but check out different repositories and different branches from there, you're able to get the code for today. And I've listed in the slides the particular versions that this is based on in case somebody in the future wants to grab this code and who may be looking at a video of this or recording of this in the future. This is based on these change sets today. So all of the code samples that you'll see later today. So the rest of this morning's tutorial, I'd like to go through the recently created example programs that demonstrate some of the functionality and highlight the MAC operation and some of the recent changes to this model. So I'm planning to cover just an introduction into some of the terminology we'll be using about what are the resources that we're trying to manage in the simulation. Then we'll talk a little bit about how user level traffic at the IP layer is routed into different logical channels, and then how those are supported in NS3. How the scheduler prioritizes between the different logical channels. How the scheduler is triggered to select resources for either semi-persistent or dynamic granting. How the sensing process works and is consulted as part of the scheduling process. And then how the harq and the PSFCH feedback channel operate currently. For introduction, if people are new to some of this technology, I'd recommend this particular document, 38300, which is publicly available, which is, I think, a good overview reference for 5G new radio. And there are two specific sections that pertain to sidelink, sections 5.7 and 16.9. And this kind of gives you an overview, and I've pulled some figures out of that document in the coming few slides. And then there are a number of different standards that are referenced in the tutorial and the code that go to the specification aspects of this. So again, we'll be talking today about a UE-based network interconnected by what's known in the standard terminology as the PC5 air interface, which is a bit different from the UU interface that separates the G node B or E node B from the UEs. So we'll be focusing really on this type of a network today. And we'll be focusing on the lower layers here, in particular the MAC layers, the presentation focus today. The PHY abstraction, I think, has been covered in other tutorials. See last year's WNS3 tutorials for a more in-depth treatment of how the PHY is abstracted in these models. And as I said earlier, the current NR is borrowing a lot from the upper layers. So it's really kind of an LTE-based model of RLC and PDCP on top of this, rather than a standards-compliant NR model here. This is part of the future work that we'd like to undertake, is to basically decouple fully from the LTE module, have a standalone NR module with no dependency on LTE, and then update to the NR specs in this regard. This diagram shows a little bit more detail, again, taken from 38300 on basically the SDAP and PDCP layers, their functionality, the RLC layer, and then the lower MAC here. So we'll be talking really about this scheduling layer here, as well as the harq. And the goal here is to be able to deliver transport blocks that queue up in these RLC entities or instances sitting on top of the MAC. So we'll talk a little bit today about how do packets that exist at this higher layer, like the IP layer, end up in one of these RLC instances, and then how they're treated in the network. Again, for more information, there is this online tutorial that I mentioned. There are also two good overview articles that I'd like to recommend. Again, these slides are posted on the workshop program page if you'd like a copy. But there's an IEEE Access article specifically devoted to the V2X extensions that was recently published. And then there's a very thorough tutorial article on V2X that I highly recommend. It's a IEEE Communication Surveys and Tutorials article. That's a good overview of the technology. Again, a comment that these are the protocol layers that are presently implemented in the LTE directory, and these are what's implemented in the NR directory below the RLC layer. And so what I'm going to focus on today really is not the control plane aspects, but the data plane lifecycle of a packet. And the reason I chose this topic is because as a developer who's been working to extend NR, I found it very difficult to really understand with the amount of detail in the models exactly what was going on to my packets. So we would see it's almost like a black box approach where you basically submit packets and they sometimes come out the other end, but it's very difficult sometimes to figure out what actually has gone on to deliver that packet end to end. So I thought I'd like to focus specifically on showing all of you exactly what the steps, sequence of operations in the models, so that if you care to look yourself or to extend it in the future, that you'll have some orientation as to what's going on. So we'll be talking again about the process of these IP packets ending up as PDUs at the RLC layer, and then how they're handled in the MAC before they're delivered off to the PHY. Okay, let me pause. Any questions, anything from online?
No questions from online with regards to the presentation materials right now.
Okay. And my audio is okay?
Yes, it is.
All right, great. All right, so let's talk about logical channels. So we're going to start at the very top of the diagram I just showed you, and let's talk about how do these packets in NS3 end up in particular queues at the RLC layer, waiting to be serviced by the scheduler. So logical channel is, I guess the way I think of it is it's groupings of packets that are going to receive similar service by the MAC layer. And there are a number of properties that can be used to classify and group these packets. I've listed a number of these here. And the idea is that if they're going to be handled and scheduled similarly by the MAC layer, you want to make sure that they basically are requesting similar service. So as a trivial example, if they're going to different destinations, you may not want to pack them in the same grants. Or if one of them is broadcast and the other is unicast, you might want to separate the logical channels there and treat them differently at the MAC layer. So these are the classifications that they're presently used, or in the standard, it describes them being used to separate packets into logical channels. And what we've done in NS3 is group these into what's called a sidelink infrastructure. And this is basically in the standard corresponding into the standard 38321, something called the sidelink transmission identification other information parameters. And we pass this to the LT sidelink traffic flow template in the NS3 code. And so basically this sample kind of shows how this is done in NS3. So we define an object called a traffic flow templates, and we create one of these TFTs later on in the code. And then we create this sidelink info parameter, and we pack all of our attributes into this parameter, assign those variables, and then pass this as part of the TFT configuration, so that packets that correspond and match against these properties are routed to a particular logical channel. And then in the stack, this type of information is propagated down through the layers, so that even at the scheduler level, it has a notion of what are the properties associated with the logical channels that are being requested for service. So you can see, for instance, here, by setting variables in the simulation program, you can say, I want groupcast, broadcast, or unicast. It'll set these parameters appropriately and then pass this structure in the code. So if you want to look, the code samples from sidelink harq info, or sidelink harq example.cc can be perused for more information here. Another thing I'd like to mention in terms of the NS3 code is how it's structured with a heavy reliance on an architectural concept called service access point. So this is a terminology used to formally describe APIs between layers and primitives that may exist, such as request, indication, response, confirm, formally in standards documents or specifications on how these layers interact with one another. And what has been done, and it derives from the history of the LTE model, which was originally based on the femtoforum APIs for small cell scheduling. They defined interfaces in this way, where there was basically a service access point user and a provider of the service. And that boundary that exists in LTE between the scheduler and the rest of the MAC is defined on these architectural principles. And similarly, these kind of APIs have then been instituted at the different layers in the LTE and now the new radio stack. So conceptually, where you have, for instance, a PDCP and an RLC layer, these software objects are actually talking to C++ classes that are of type LT RLC SAP user and LT RLC SAP provider. So for instance, the PDCP layer, when it wants to deliver a packet down to the RLC layer, it doesn't have a pointer to an RLC object specifically. It has a pointer to an LTE RLC service access point provider object, which then forwards information to whatever implementation sits underneath this. In this case, the like an RLC unacknowledged mode instance of the class. And likewise, the RLC will be delivering up to the PDCP layer through this type of a SAP user interface. And so if you look in the code, you'll see many instances of this. And this is, in my opinion, one of the difficulties in working with this code is understanding how this is all plumbed together and the constraints that these kind of interfaces offer on what layers can see or do with respect to information available at other layers. So the ones that I'm most familiar with are the MAC and the PHY, this MAC SAP user and SAP provider classes, as well as the physical layer ones. And then similar ones exist between the MAC and the scheduler boundaries, although we may be removing those in the future. And so what this looks like in C++ is that, for instance here, these model objects that are implementing the functionality that we're talking about, like the NR UE MAC layer, they include these API objects that act as forwarding objects. And these are all tied together using callbacks to access these APIs. And the classes known as the helper objects that exist in the helper directory are the ones that make all of the connections during simulation setup time. So if you look at this snippet of code with the NRUE MAC object, you'll see that there's two methods here, get PHY SAP user, which returns a pointer to an instance of this class, and set PHY SAP provider, which is basically setting the pointer for the physical layer that whenever it needs to consult the physical layer, it will go through this PHY SAP provider pointer. So if we look at the implementation of these particular API classes, you'll see that, for instance, the UE physical layer SAP user class has a number of methods that are, has a number of methods that are exposed. And this is really all that the MAC layer is able to do at the physical layer. It's able, this is all that the physical layer is able to do with respect to the MAC layer. So it's able to pass up a PHY layer PDU. It's able to pass up a control message. It's able to note that there's a new slot starting and passing up this or making available this getter method as well. And other things that might be available at the MAC layer are inaccessible directly through this interface. So when we want to do extensions to get more information to enhance our models, typically we have to plumb them through as new attributes or parameters through these APIs. And then if you go look at the actual implementation of one of these objects, they're basically forwarding objects that forward to the public API methods. So for instance, the implementation of receive a phi PDU calls on the MAC layer an instance of a different method, do receive phi PDU. And it has privately, it just holds a pointer to an instance of this NRUE MAC. So anyways, I wanted to introduce this just because if you go to try to look into the code, you have to be aware that as packets are passed through the layers, they don't pass directly from an instance of one layer object to another. They go through some of these APIs. And as I mentioned earlier, certainly between the MAC layer and the scheduler, we may be taking these apart. I think it's for further discussion whether also we retain these in the future in the NR module, but that's how it's implemented presently. Any questions on this aspect? I have a text here. Oh, I'm not pretending to this. Okay. All right, let's talk a little bit about sidelink resources. So in a new radio network, the available bandwidth can be split into different bandwidth parts, which may be differently configured. They may have different numerologies associated with them. And within this bandwidth part, there's a capability for sidelink to define what's called a resource pool. There can be multiple resource pools defined. They can be segregated, that groups of UEs could be serviced by one resource pool, and a different group of UEs could be defined to be using a different resource pool. They could be also partitioned so that one resource pool was used by certain UEs to transmit and they listen in another resource pool. But that's what the terminology means. And I'll go a little bit into more detail in the coming slides as to the specifics of what are in these resource pools. But if we look at just from a time frequency perspective here, these resource pools are made up of slots in the time domain, and then what are called subchannels in the frequency domain. And the subchannels are basically our collections of contiguous physical resource blocks. And the standard allows the definition of the number of physical resource blocks that are associated with what's called a subchannel. The subchannel is the smallest unit of granularity that's scheduled upon in an LTE network. So scheduling does not occur on a PRB boundary, but instead on a subchannel, whatever's configured for that particular resource pool. Similarly, the minimum granularity in a sidelink network is a slot. There's not the capability like you may have in the uplink and downlink networks to have many slots. Only a full slot is kind of the time domain granularity here. Within the slot, if you look at the standard, and these diagrams are very nice. They're from this communication surveys and tutorials paper. There are different ways that the slot can be structured. Slots typically, they'll either have 12 or 14 symbols available. These examples, and also there's a case for, oh yeah, I think these are all 14 symbols in this particular configuration. I think it depends on whether the configuration of the cyclic prefix at the physical layer. If you look at the slot structure, you'll see that the PSCCH, the control layer physical channels, typically start in the second symbol, and they either will last in the lowest indexed PRB, and they'll either last for 2 or 3 symbols, depending on the configuration. The blue elements are for the shared channel for data. And then periodically, there are these demodulation reference signals that are inserted as well. So only a subset of the total number of symbols are available for sidelink traffic. And one of the things in terms of scheduling, if we're scheduling across a slot, we need to know how many symbols are available for data. And depending on how things are configured, there could be different amounts of symbols available for traffic, leading to a different capacity for that configuration. We have a simplifying assumption in the code that I'll talk about today, that there are uniformly 9 symbols available for data, regardless of whether the PSFCH is present or not. You can see that in this particular slot here, that the presence of this feedback channel basically eats up 3 additional symbols from the overall slot structure. So including this feedback channel causes a reduction in the capacity of a slot. So for this reason, the feedback channel is not always repeated in every slot. There may be a periodicity as to which slots have feedback channels in them. But in the NS3 code, we do respect the PSFCH periodicity. So you can configure it to have either not be there in every slot, every other slot, or every 4 slots according to the standard. But regardless of whether it's there from a capacity calculation perspective, at the moment, we're always assuming that there's 9 symbols available. This may be enhanced in the future. Any questions on this? Okay, so moving on. This is a figure taken from Zerez's paper. I think it's also available in last year's tutorial. This shows with a little bit more detail how these resource pools might be constructed. So if you look, for instance, this is frequency on this y-axis, and it's configured so that there's approximately 10 PRBs in this subchannel. And what we'll see is that there's a time pattern here expressed with the characters D for downlink, F I think is for flexible, U for uplink. So there's overall imposed and configured on this channel a pattern that some of these slots are used for downlink traffic, some for uplink traffic, and some can be flex between them. And then we're only concerned with sidelink here. And so what's done is that there's what's called a sidelink bitmap that's overlaid on top of the available uplink slots. So everything that you see here in green corresponds to a slot that's available for uplink. And so the sidelink bitmap pattern may reserve that certain slots are still available for uplink traffic, and certain are reserved for sidelink. So if you look at it in the code, in the way that this is expressed in the standard, you'll see a bitmap pattern where if there's a 1 associated with an uplink slot, then that means it's eligible for sidelink. And if there's a 0, that means this is just strictly an uplink allocated slot. And these will then repeat. So there's an overall periodicity of the TDD pattern and the sidelink bitmap. And so what this is depicting pictorially is that because of this particular pattern here, these are in green are the available resources for sidelink. So what we see here is that there's 2 subchannels available. And then these are the slots over time where sidelink data could be inserted. How this is defined in NS3 code, you have to, in the current examples, it's basically organized in a couple of different places in the code. I pulled this out of, I think this is common code for all of our V2X examples, where there's setting of the numerology, setting of the subchannel size, and then the sidelink bitmap patterns. So what I just showed you in the previous slide could be represented with something like this. A representation of what is the bandwidth according to for this frequency band. And then there's something called a component carrier bandwidth part creator that basically takes all of these parameters like the central frequency, the bandwidth of the band, the number of component carriers, the type of, this is basically passed into the channel configuration, and then configures the underlying physical resources according to this kind of parameterization. So it's really the combination of these parameters that defines the resources that the Mac has to work with. And I guess one of the comments that I have in working with this code is that it's probably would be helpful if we had some guidance as to what are the reasonable values to use in the NS3 simulation. Because if you think about what we're doing here, we're going to be looking at, for instance, latency performance, and it's the latency performance is going to be dictated by how many resources are available. So you can construct your simulations by picking very large values here and not have any problem scheduling anything, or you could end up creating a lot of problems if you don't allocate enough. And as far as I know, there isn't any guidance into how to configure these for meaningful simulations. It's a little bit different from my experience in Wi-Fi, because certainly, I mean, Wi-Fi is trending in this direction, but legacy Wi-Fi, you knew that, okay, I have 20 megahertz channels and I had these MCSs. So I know specifically, like with a commercial Wi-Fi network, what I'm able to get out of it. And here, because I can basically define all of these parameters in different ways, I can kind of dimension my problem however I want. So I think there needs to be some instruction or guidance to users as to what are reasonable real world numbers that we should be plugging in to configure our resources. So anyways, if any of you have any insight as to how this is done or references on, you know, here's typically how this would be provisioned in a certain type of network, I'd like to learn some of that information. Okay, any questions so far? Yes.
For that sideling bitmap, if there's no sideling information, does that revert back to
So does it revert back to uplink? Well, in the simulations that we're running, it doesn't matter because we're exclusively mode 2. So there's no Gnode B involved in it.
But
if there was no sidelink traffic, well, I don't know whether it would revert, because just from your perspective of there's no traffic, it may be being used by other nodes in the network. But I don't know in practice whether there's dynamic reallocation of these slots. Yes.
I know this is asking questions. So for you to move the vision, do they have some kind of consensus pattern to know the bitmap pattern, or is it baked into the hardware or something?
So the question is there any consensus as to what the bitmap pattern would be?
Do you come to a consensus together?
No. So I guess the question is this a dynamically worked out consensus protocol to figure out the bitmap? To my knowledge, it's not. This is kind of it's defined as like a pre-configuration step. So I think that it would just be provisioned. I don't know whether in practice there's mechanisms to agree on that with a consensus. Okay. The standard talks about multiple bandwidth parts and multiple resource pools. It's not covered today, but it is possible to define multiple bandwidth parts in the simulator and multiple resource pools. You could also assign different numerologies to the different bandwidth parts. That would be one of the, I guess, rationales for doing this, because you might want to offer different latency performance based on the configuration of the numerology. But on all the examples we've been looking at, we've just been using a single bandwidth part and a single resource pool. In NS3, if you do define multiple bandwidth parts, then you need mappings between these logical channels and the bandwidth parts. And this is handled in NS3 with something called a bandwidth part manager algorithm. And presently, there's only a static mapping in the default implementation that's provided that's based on a bare QCI value. So you could basically, in principle, you could configure that certain QCI values are going to be mapped to a particular bandwidth part manager and others to a different bandwidth part. And it looks to me that this has been experimented with on the uplink and downlink code, but I'm not aware of this ever being tested or exercised in the context of V2X. So we've just been focusing on single bandwidth part and a single resource pool. But there are hooks in the code. If people are interested, I think there may be some capabilities, at least for multiple bandwidth parts and the mappings between them. Okay, so with this kind of as a background, so the resources that we have are these sidelink slots and subchannels. And now we're going to talk a bit about how scheduling actually works in the models. So consider when a new PDU arrives, there's a notification given to the scheduler. The scheduler has to find future resources that, first of all, don't conflict with its own scheduled transmissions that may be serving other logical channels. They do not conflict with any planned receptions. So they might be in the be listening, have an application interested in receiving data from other senders. They want to ensure that, or try that there's or minimize, let's say, the collisions with other UE transmissions, and take advantage of the knowledge about who is transmitting when. And then we also want to allow for retransmissions and feedback. So all of these factors go into picking resources for this newly arrived PDU that has to be scheduled. And additionally, each UE's interference environment can be different. And so in this small diagram here at the bottom, I consider that all of these UEs exist in the same network. And it could be the case that these two UEs are far enough from these two UEs that silent communications could occur on the same channel, or sorry, in the same resources. But because of the proximity of these nodes, they're not able to reuse the same resources because it would cause interference. So just keep in mind that the problem that we have is that everyone's view of the network and the interference that exists in the network is somewhat unique here, and that has to be accounted for in the algorithm. Finally, modulation and power control could be factors as well in terms of trying to schedule and optimize the use of resources in this network. In the NS3 code, our schedulers are not dynamically changing the MCS. This is a fixed parameter in the NS3 model, and it's also not doing power control. But I think that the capabilities are there that it could be expanded to do that in the future. And from my perspective, this kind of problem is one of the more interesting problems that you can use a simulator like NS3 to study. And it's a rich problem because, as you can imagine, there is just a lot of parameters that could be optimized. And the scheduling problem for this is difficult, which makes it, I think, a fertile ground for a lot of research. And we'll be hearing a little bit about some of that research in the next tutorial. And so we just talked about this is what the scheduler has to do. It has to figure out what's going on within its interference environments, and then it has to plan for whatever data it's anticipating from this particular sender. And so the way that this is set up is that there's basically two windows that it's using in its algorithm. One's called a sensing window and the other's called a selection window. So again, I have a time frequency layout here. And consider that we're at time n on this diagram here. And there needs to be a scheduling operation done for a packet that's just come in. And future resources are depicted here on the right. And what's happened in the past is depicted here on the left in blue. So what's defined is what's called a sensing window. This is a number of slots that occurred in the past. And basically the scheduler asks, in the standard, it talks about asking the physical layer to provide information about what transmissions were decoded in this within this sensing window. And then the selection window is where it has to pick resources for this transmission. Now, this selection window is bounded by a couple of constraints here. So first of all, conceptually, these packets have what's called a packet delay budget. So this may be, for instance, 20 milliseconds. Because of the latency of the application, we need to find resources for this within 20 milliseconds. So obviously, we don't want to schedule resources beyond this delay budget. And then there's also a processing delay. So we can't necessarily schedule resources for the next slot. So basically, there's two parameters here called T1 and T2 that govern the length of the selection window. T1 is like 2 or 3 slots in the future. So you're assuming I can't schedule for the next slot, but maybe 2 or 3 slots from now is the first one that I'll be able to schedule this new PDU on. And then I want to do it before the packet delay budget expires. There's another parameter called T2 min in the standard. And this basically influences where the edge of the selection window will be. And this T2 min can vary depending on the priority level of the traffic, so that you could basically force higher priority traffic to tend to be selected sooner in time than later. On the left-hand side, we have parameters T0, which is a configuration parameter, and another one called tproc0, which again, I think it represents a processing delay. So we look back in the past history. I think in many of the examples we're talking about today, this might be 100 slots, and we're going to make decisions on the selection window based on what's observed in this sensing window. So we're going to use a couple example programs to demonstrate how this is handled. The first one is authored by Samantha, and I'll be talking about that one first. This is focused on her work to extend the scheduler to handle multiple logical channels and also dynamic grants. And then I'll talk a little bit about a sidelink harq example later. Both of these programs derive from an original program that was written by Zares. And then in the examples here, I'm going to print the output of some simulation commands, and I'm going to put all of those commands in a box here, depicted in this Courier font and enclosed like this. So this is going to be my convention for showing you some of the simulation output. So let's just take an example and walk through what happens to the packets in this example. So this is just a description of what this simulation program is doing. This is demonstrating how different sidelink traffic profiles can be configured and then how they could affect resource selection. So this topology in this example is very simple. There's two UEs separated by about 20 meters. And there's 3 traffic flows. And each of these can be configured differently from the command line. The assumption is that there's constant bitrate traffic. The default is 16 kilobits per second, 200 byte UDP packets. And there's no hybrid ARQ configured. We'll talk about that later. But blind retransmissions are enabled, which means that for every packet that's sent or every transport block, it can be repeated a number of times and then reassembled at the physical layer to help improve the reliability of the channel. There's a number of traffic profile parameters varied: the scheduling type, the destination layer 2 ID, the priority, and then there's also a flag that basically is a tiebreaker flag, whether you, in the cases of a priority tie, whether you would give priority to semi-persistent scheduling traffic or dynamic grants, and then the resource reservation interval. And by changing these values at the command line, you can basically force the scheduler to schedule these logical channels together or separately. Okay. Oops. So if you run this program, there's not a whole lot of output that's displayed by default. There's, for instance, if you just run it with no arguments, you'll see that there's 60 packets sent and received, and there's a computation of the average packet delay across all the packets. This is measured at the application layer. The program also populates an output file, which is a per packet record of the time every packet was sent, and then the delay that that particular packet experienced. So you can read this if you want to get the per flow latency for these different flows. And this table represents, and this is actually present in the comments in the beginning of the program, how if you set this various parameters at the command line to different values, you can affect the traffic profile configuration per flow. So as an example, if you're setting the scheduler type config to the integer 1, that means that all 3 flows will be configured for dynamic RAM. And if you set it to 2, then the first will be, or all 3 will be set to semi-persistent scheduling. And so on. So you can see that basically by picking different values here, you could force these flows to have the same or different attributes. Okay. So one thing that Colin and Lou will talk about in the next tutorial, and I haven't covered much here, is the difference between semi-persistent scheduling and dynamic grants. Originally, semi-persistent scheduling, that's the initial mode of traffic that was supported by CTTC. If you go to the public release of CTTC's V2X, there's only a capability to schedule semi-persistently, which means that there's assumed to be a periodicity in the application traffic that you can exploit in your scheduling. So the assumption would be that, let's say, every 20 milliseconds, I'm going to generate a new packet. I think a lot of broadcast type situational awareness applications may work like this. And the scheduler makes use of that by, as we'll see, scheduling consistently. If it's expecting traffic to arrive every 20 milliseconds or every 100 milliseconds, then it will devote and reserve resources in the future for repeat packets from that flow. But in many applications, there's also, let's say, stray packets or packets that aren't associated with a regular periodicity. And we call that the need to schedule those as the need to just generate a dynamic grant, which is a one-time grant. It doesn't repeat in the future. It's only responsible for delivering that particular packet, which becomes a transport block in the new radio stack. And then it waits on that logical channel for another packet to come in, and then it just on demand is making scheduling decisions for whatever comes in with no future reservations. So that's the new capability that Samantha recently introduced called dynamic granting. And the more V2X-ish type of traffic is handled by what's called semi-persistent scheduling. Okay, so I'm going to walk through a flow of what happens in the simulation models in this particular example. So the RLC gets some data that's been basically, as we mentioned, filtered to it by configuration of the sidelink info parameter. It generates what's called a buffer status request down to the MAC layer. The MAC layer forwards this over to the scheduler. And then the scheduler updates the data structure corresponding to that particular logical channel. So this is the technique by which the scheduler is informed that there's data pending at the RLC layer. And so I'm going to show you then some snippets of, if you enable NS3 logging, how you can observe these operations in the simulation output. And let's see. I'm going to step through this slide. Oops. In a little bit of detail here. So this is the command that I'm using to run this program. So if you're familiar with NS3, you're probably familiar with running something at the command line where you use the NS3 Python program to run an executable. So usually this is how you would interact with NS3. NS3 run this program name, but I'm prepending this statement with a configuration of a special environment variable called nslog. And this is just for demonstration purposes. And I'm going to step through all of the elements of this particular command that I'm using. I'm showing you this command because I actually make use of this a lot in my day-to-day workflow of being able to use logs and selectively enable things to see what's going on in the program. So the NS3 logging can be controlled by C++ statements. So we actually have a C++ API that you can basically build this into your program. But the downside of that is if you want to make changes, you have to recompile your program, or you have to expose command line arguments to catch this. So when you're basically trying to work without rebuilding all the time, you can exploit this nslog environment variable, which then can control what log elements are turned on and off. And each logging component is defined in an implementation file, and you can specify multiple of these. In other examples that I'll show, you can separate these by colons. So you can selectively say, okay, I'm interested in the scheduler, I may be interested in the MAC, the harq, the physical layer, whatever you're interested in, you can basically enable just those components. If you enable too many components, you could drown in output. So you have to be a little bit surgical into what you're trying to look for. Similarly, there's multiple logging priority levels. So people familiar with logging frameworks in C++ or Java are probably familiar with seeing code where there's logs defined at different levels like error, warning, info, debug. The levels that we're using in the NS3 code are warn, info, function, logic, and debug. And I recently pushed a commit that'll be in the latest NS3 release. I'd like to go through a lot of our models and filter out and focus on making the info level the level of debugging that will show the key events going on in a model, and then moving some of these other logging priority levels lower, such that if you really want to see the gory details of what's going on, you would enable something at a lower level like logic and debug. So in the code that I'm showing, I've gone through the logging statements and I've picked out key, I guess the way I typically characterize it is if the model is changing state, I'll report that state change in an info log message. And then other things like, showing the iteration of an algorithm, the loop in an algorithm, those would be logged at a lower priority level, such as logic or debug. So I'm going to focus here on the info level because this produces a more manageable amount of output. There's a number of logging prefixes that can be used to annotate the output. So I'd like a timestamp. I'd like an indication of which node it corresponds to. and what is the function where that statement was executed. So you can tailor this as well. And I want to redirect all of this into a file. So typically, if you just enable logs, you'll see a bunch of text rush through your terminal, and you'll have to scroll up to find what you want. So I typically redirect it using standard bash techniques into an output file. And since it's all printed out on Sierra, I redirect that to standard out with a command like this. So if you execute this, this will turn on the scheduler logging at the info level with these prefixes. It'll dump it into a file called log1.out, which I can then use a text editor to look at. So we just showed earlier here this flow, 4 steps here. The SDU arrives, buffer status request, coming to the MAC, going to the scheduler, and then updating this data structure. So if you run this command and you look at this output log file, you can see, well, to see the first step of the SDU arriving, I would need to enable the logs in the LTE module. And I haven't done this in this example, but these are the statements that you will find in this file. On line 17, you'll see a statement here saying that here's the buffer status request arriving at the MAC object at time 2.1 seconds. And the queue size is 235 bytes. So this is with overhead added to that UDP packet. And then the next line shows that the MAC is then directing this over into the scheduler. And basically the scheduler is logging that, oh, I got data in for this logical channel, which I'm using as index 4 in my model. And then if you look further, then it'll basically there's another scheduler class handling all of the logical channel data structures. And there's a update logical channel call that basically says that, yes, I've stored that information for future reference. Scheduling decisions are not made yet. This is just the scheduler collecting information from what's going on at the RLC layer. So the scheduling occurs on a slot boundary. So every time in that diagram where I showed there was a new slot starting, there's an indication given to the MAC layer that a new slot is starting. So what happens is that the MAC will send over to the scheduler what's called a trigger request. And the scheduler will then take a look at its data structures and determine, do I have any new data pending at the RLC layer that needs servicing? And so if the answer is yes, it goes into the scheduling process. Given that there may be resource constraints, there needs to be a prioritization mechanism implemented. And so that's the next step, is figuring out among the logical channels that need to be scheduled, which are the ones that I should prioritize. And this is code that Samantha recently implemented, and I think she can clarify if there's anything she wants me to add here. But basically what's done is that the logical channel prioritization can be handled by first looking at the priority of the logical channels. And this can be used as a primary means of prioritization. And when logical channels have the same QoS priority, then we need to add some other heuristics. So it could be, for instance, closest deadline to the packet delay budget, which queue has the largest backlog, which one was the longest time since it's been allocated, or it could be like a round robin scheduling policy. So some high priority LCs may not be able to be scheduled if there's congestion, but there may be congestion because there are pre-existing grants to lower priority logical channels. So there's a feature in the standard called preemption, which could override this and cause the scheduler basically basically to give priority to this new traffic. This is kind of the view of the general problem. Not all of these features are implemented in NS3. So for instance, preemption is a feature that we don't support yet. I'll talk now about what the code is presently doing, thanks to Samantha's implementation. The current implementation will sort destinations, and then within each destination, because that's how the data structures are organized in the current scheduler, it will select and sort by logical channels according to the priority and some additional heuristics. So first, it'll go through and look at all the destinations, and it'll find the destination that has the logical channel with the highest priority to be scheduled. And if there's a tie, then it will select the one with the smallest destination L2 ID, just as an arbitrary tiebreaker. And then within that destination, it will select the logical channel that has the highest priority. And then it will select all the logical channels with the same grant attributes as that one with the highest priority, so that they could basically be scheduled together. And if there's a tie between different scheduling types that otherwise, or different traffic types that otherwise have all the same parameters, then there's an additional flag that's used, whether you would give the priority to semi-persistent scheduling or dynamic grants. And then the final step here is, this is kind of obscured if I can move this. And if in the end, if everything is about the same, there's basically the last tiebreaker is the lowest logical channel ID, if every other factor is the same. Okay, any questions on this? Colin, have any questions come in on the chat?
None with regards to the PowerPoint.
Okay. All right, so let's proceed then. All right, so let's look at this trigger request. So again, this is for future reference if you want to reproduce this. I've had to drop down in the log level to the logic level in the scheduler to see some of these log statements because the info is not exposing that presently. And the debug level at the NRUE MAC. So the slot boundary occurs. That's logged. So notice that once I turn on these lower levels of logging, that now I have tens of thousands of log output. So time 2 in the simulation, I'm already at line 39,000 in this text file. But anyways, what I'm searching for here is this statement that says, here's the start of a new slot boundary. This slot boundary happens to occur after the RLC has been enqueued to. So that means that there's something for the scheduler to do. So this trigger request goes across. There's a note, there's one destination needing scheduling. And then if you look at the details here, prioritize the logical channels in the scheduler. It basically reports, I have 3 logical channels with a total buffer size of 705 bytes and requiring 1 subchannel for an overall transport block size of basically 1,300 bytes. And then if you look through the log, you can see all the operations pertaining to scheduling that. And then finally, at the very end, it says all logical channels of destination 255 were allocated in this example. These were all allocated together because by default in this program, they all have the same characteristics, all of these flows. And this slide basically shows that. That's, if you notice all of these defaults for the value 1, they uniformly have the same across all the flows. So in testing, what we've been doing is varying these values so that we can get different flows to have different characteristics and just checking the execution of the algorithm. Okay, so let's continue. So now let's assume that the scheduler has picked what it needs to schedule. It now needs to make the resource allocation. So the way that it does that is the step 4, it requests the candidate resources from the NRU Emac. And this launches the sensing process. So the sensing is based on a combination of the control channel traffic that's been decoded in the sensing window and the RSRP that was measured in these slots within the window. Now, one of the assumptions in the model is that this is a half duplex device. So nodes cannot transmit and receive in the same slot. And so that factors into how resources are selected, as I'll explain in a slide or two. The sensing for sidelink mode 2 is specified in a 6-step algorithm in this 3GPP standard, and the NS3 code follows that algorithm pretty closely now. I'll just walk through what's done here. In the standard, that's described as a MAC-PHY interaction, where the MAC basically provides a number of inputs to the PHY. It says, here's the resource pool I care about, the priority, here's the packet delay budget, the number of subchannels that I need contiguously to be scheduled, the RI, and a reselection counter. And then the output from the PHY is a set of candidate resources in that selection window that I just showed. And in the NS3 implementation, it actually doesn't recurse down to the physical layer. What's done instead is that whenever there's a successful control channel reception, that information is conveyed to the MAC as sensing data, and that sensing data is stored in a buffer at the MAC layer. So in the NS3 implementation, it's not going into the physical layer, but it's basically going into a sensing database, and the algorithm is executing as part of the NRU MAC in the NS3 model. And in the implementation, this is the method here, get NRSL candidate resources private, which implements the nuts and bolts of this algorithm. It's specified in section 8.1.4 of 38.214. And here I've built a table that shows the specification term and then the variables in NS3 that correspond to all of these. Most of these are supported in the code. There are some features that aren't currently supported, specifically some of the thresholding in the standard basically could be configured to be different based on the different priority levels of the traffic. We use a uniform one across all priority levels. There's an option to specify which channel, whether the control channel or the data channel to use for your RSRP measurements. We're only using the control channel. Sorry, this is a typo. This should say PSCCH here. So we're not supporting this option to use the PSSCH for sensing. We're using the PSCCH. The resource reserve period list can be retrieved from the pool object. The other thing we don't support is a list of basically per priority value levels of a resource percentage to compare against. We only have one across all priority levels, and we don't support preemption. But pretty much everything else we do support in this algorithm. We had to make an interpretation of what we mean by all candidate resources. So this is a simple example to depict how we defined it. So we have slots on the x-axis here, subchannels on the y. There are 8 candidate 3 subchannel single slot resources in this block here. So let's assume that there's a request for a resource with 3 subchannels. I could start at this lowest subchannel. Say it's index 0, 1, 2, 3. So one of my resources that I could deliver as a possible resource would be this set of 3. Another one would be this set of 3, starting with index 1. Notice that these can overlap. So if you look at this particular grid, there's actually 8 ways I can construct contiguously in a single slot, 3 subchannels that are adjacent to one another. And so these are, in this particular dummy example here, there would be 8 single slot resources to consider here. And the reason to do it this way is that you could have, for instance, in this slot, maybe someone is using this lowest slot, but I could still squeeze in my allocation in these upper 3 subchannels. Sorry, so someone's using this subchannel, but there's still 3 available. So this would be a case I could select this group of 3, but not this lower group of 3. Okay, so the job of the sensing is to define and pass a list to the scheduler of all the candidate resources that are in the selection window that are eligible. And in this example, assuming nobody else is transmitting and there's no interference, it would say there are 8 candidate resources. And so the way that the algorithm works is that if you go look at it, you initialize the set to all candidate resources to start. And then the next step is what's called step 5 in the standard. This handles the half duplex assumption of the UE. If in the past, in that sensing window, if the UE had been transmitting, then it could not hear what somebody else may have been transmitting on that slot. And so what the algorithm does is it looks at all such slots, and it basically will consider the possibility that maybe somebody else was using a resource in that slot, but it doesn't know what the scheduling properties were of that resource. Maybe this is a semi-persistence scheduling resource that's going to repeat multiple times in the future. So let's say that it's possible that it repeats every 100 milliseconds. The scheduler is going to make, or the sensing algorithm is going to make a conservative assumption that somebody out there may have been using that slot and may have sent data that's going to recur every RI interval, in this example, 100 milliseconds. So it's going to take this conservative or pessimistic view. Furthermore, every resource pool may be configured with a number of possible legal RI values. It may be every 20 milliseconds, every 50 milliseconds, every 100 milliseconds. So it basically has to enumerate all the possible combinations of this and conservatively assume that, well, maybe somebody was out there that used a resource that's going to recur at these different patterns as well. So it basically goes into the selection window and blocks off all of these slots that correspond to possible transmissions that it missed. And then what it does is, once it's done all of that, it goes and looks at selection windows, and it looks at how many candidate resources are left. And if the resulting number is less than a particular threshold percentage, and there's 3 values in the standard, 20, 30, and 50% that can be configured, then what it does is it basically throws away all that information and restores all the candidates to what was originally in the pool. And the idea here is that the scheduler or the sensing algorithm will try to, if there's enough resources available, try to avoid any possible resources that might have been used by somebody while I was busy transmitting. But if that becomes too onerous a burden on the selection of resources, it basically forgoes that and just worries about the signals that it actually has decoded. And that's step 6 here. So otherwise, it goes and looks in its sensing window and it looks at what it successfully decoded, the control channel, which will have an SCI 1A message, which will actually points to additional resources that are being used. It will also indicate the RRI and the reselection counter on these resources. And basically what the sensing algorithm will do next is it will look at all of these and it will compare the RSRP power value that was measured with a threshold. And if that came in above the threshold, then it excludes the future projections of those resources that observed in the sensing window into the selection window. And again, what it does is it runs through the sensing data and it takes a look, how many resources do I have left in the selection window? And if this is less than this threshold percentage, it goes back and says, okay, I'm going to rerun the algorithm. I'm going to increase my threshold by 3 dB and repeat the whole process again. And the basic idea of what's going on here is that it tries to run the algorithm enough times so that it meets a threshold number of candidate resources. And if it can't do it at the first pass, it progressively throws away the weaker signals until it arrives at a resource pool that is large enough that it can hand over to the scheduler. So this will result in the scheduler, I guess, doing the least amount of damage or interference to other transmissions that may be using that resource pool. So I'm not going to show the simulation code that executes this, but if you look in that implementation, it follows the specification very closely. So once these resources come back, the scheduler further has to filter these candidates for already allocated resources. So there may be other logical channels that have been scheduled and they haven't transmitted yet. We're not going to also schedule to use the same resource. So once these have been filtered by the scheduler, it'll have a pool of available resources that it can now pick from. So then it'll schedule the grants and it will, I'm sorry, this is hidden by this ribbon. And it will schedule any retransmissions that need to occur. This is a depiction of a slide that I actually borrowed from Richard and from a NIST presentation. So this pictorially is showing what's I just described. So let's assume at this time point, higher layer requests available resources for the transmission. These are the subchannels and these are the slots. These are the sensing and selection windows in this example. And let's assume that in this sensing window, there was a SCI1, a control channel transmission, as well as a traffic transmission in this particular slot, and that this also pointed to transmissions that were occurring in these future slots. So these subchannels were taken by some other UE in the network. What is then done is that based on this, the reservation period here, it projects that I observe this traffic here. I know that this scheduler for this other UE will be transmitting here. And in the future, I can guess that it's going to be transmitting here and also here as well. So these are examples of resources that I want to work around. So these resources then are marked with X. They're excluded due to the possibility of direct collision. And then the reservation period, let's say I want to select a resource for this PDU. Let's say I want to select it here, and I know that I have a particular periodicity of my traffic. I need to check in this selection window whether future transmissions, if I grab this resource, whether it's also going to be free every time it needs to repeat. So I need to make sure that not only the first instance of my resource that I select is clear, but also future repetitions of it in the case of SPS scheduling. And then also the other slots that may be selected, I need to make sure that those also, the repetitions of those don't collide with other ones that may be scheduled. And so it's going to basically randomly select here. If these are all like, these are my, I think in this future transmissions that are scheduled, these are exclusions due to the sensing data, then I have to pick from what's left. And the resources then are selected throughout this reservation period. And then I'll just skip this. This is a similar example. So the sensing algorithm was implemented in NS3. It's in the current V2X branch code. But the enhancement that was recently made is that the currently publicly available sensing algorithm only works assuming that there's only one subchannel. So basically it considers a resource to take all the subchannels in a particular slot. And we noticed that if you run simulations where there's only a single subchannel, that the existing algorithm was working. But when you have multiple subchannels, you need to be able to distinguish the resources across subchannels and frequencies and not just slots. So in this particular example, this is actually an example that I use in the test code where I've artificially filled one of these subchannels with sensing data so that all the resources are taken in subchannel 0, but none of them are taken in subchannel 1. And then looked at what resources are available in the selection window. And in the previous or the current code that's on CTTC site, the current release, this type of allocation will block all resources in the selection window until you iterate it, until all of these are ignored by the algorithm. But in the new code, it will basically on first pass, it will ignore these resources in the selection window, but it will allow scheduling because these are empty in the sensing window. That's kind of just a, I guess, a trivial example that demonstrates the difference between the code we're talking about here and the last release. Okay. Any questions? All right, let me step through a couple more slides and then we'll take a break. So these features are not implemented in the current schedule right now. Reevaluation, preemption, handling of differently sized slots, as I mentioned earlier. For the transport block size calculation, it becomes difficult if you assume that some slots or some of those resources I showed have different capacity than others. So the current code basically makes a conservative assumption that all slots are uniformly available for with 9 symbols for data. We may relax that in the future, but that's presently the way that the scheduler works. And so finally, what happens is that the scheduler publishes the grants to the UEMAC. The UEMAC sends a notification up to the RLC layer saying there's a transmit opportunity. Traffic is dequeued, stored in the harq buffer for sending out later. And you can see this in the log output, again, logging at the info level on the scheduler and the MAC. That's a statement like this. The there's a config indication primitive that's passed from the scheduler to the MAC that there's grants to publish. So in this initial example, I'm publishing a grant to destination, this destination 255, which is a broadcast destination, and using a harq ID of 0. And then what the MAC does is it basically notifies the RLC of this transmit opportunity on this particular logical channel for this amount of data. And then the RLC uses this notification and sends that packet down into the MAC, which will then store it for when the grant actually executes. And if you look in the log, there's more information provided about the grants. There's, for instance, this is a dynamic grant, and there's blind retransmission. So there's going to be 4 repetitions of it. So you'll see that it's basically saying at this frame, subframe, and slot, there's reservation for that grant. And then there are 4 additional repetitions in future resources for satisfying that particular dynamic grant. And then what happens is that later in the code, when a slot boundary occurs, it checks, in this example, am I at one of these times where I'm supposed to be sending data? If so, it will basically prepare, if needed, the control channel message, and then any traffic channel messages, and send them down to the physical layer. And to do that, it's already stored this data. So this data has been dequeued from the RLC layer. It's sitting in a harq buffer here. And basically it'll reach into the harq buffer for that process ID and pull the packet out and send it down to the physical layer for transmission. And so you can see this in the logs here, that here's this first transmission. And again, there were 3 PDUs from 3 different traffic flows that are satisfied by this grant. And then this SCI1 message, which indicates the presence of this transmission, and then these 2 first retransmissions. And then later in time, there's a transmission of another repetition of this, 3rd and the 4th. And then there needs to be another SCI1 message associated with these last 2 retransmissions. And you can see all of these occurring in the log. Okay, I think this is a good break point. Why don't we take a 20-minute break and come back at 11, and then we'll go for another hour and a half. I'm going to wrap up by talking about what's been implemented for harq, and then we'll hand over to Colin and Lou for the second presentation. Any questions? Colin, any questions on your end?
Yeah, since we're taking a break, can you answer really quickly sort of when and where the conference will be posted, the video?
The video will eventually be published on our Vimeo site.
Okay,
I don't know the date yet.
that's fine.
I'll send an email around to people when it's available.
Okay, thank you.
Okay. All right, we'll be back then. I'm going to mute here. Back at 11 o'clock local, top of the hour. All right. So everyone online, welcome back. So we're going to run for another hour and a half. I'm going to wrap up this tutorial presentation over the next 30 minutes, and then we'll have another presentation from the University of Washington on resource allocation. And let's go back to our slides. And thanks to Juan, we have figured out how to hide that ribbon. Now, how can I? Yeah, that should be better. Okay. Any questions since the break? Any questions from online?
No.
Okay. All right, so I'm going to wrap up. I've talked about the sensing and the scheduling, the new support that was added, just to summarize, sensing across multiple subchannels, scheduling for dynamic grants in addition to semi-persistent grants, scheduling also for multiple logical channels instead of just limited to a single channel. This was necessary to support some of the ProSay simulations that will be talked about in the afternoon. The last piece is hybrid ARQ, which I've hinted at earlier in the presentation. This is a mechanism in the Mac to repeat transmission of transport blocks a number of times until the remotes acknowledges them. In the standard, there's hybrid ARQ defined for both the uplink and the downlink. There's a bit different process for the sidelink, but fundamentally it's similar to those other modes. It's defined in the standard for unicast and groupcast. There's not much mention in the standard that I could find for blind retransmissions, but this is the initial mode of harq that was implemented in the CTTC V2X branch. And again, blind retransmission doesn't have any acknowledgements whatsoever. The scheduler will just blindly pick retransmission slots in its schedule, and it will schedule to send for a configurable number of times up to 32 transmissions, depending on the configuration. And it will just pick resources randomly within the selection window. And there's some work that has been done recently by NIST on a physical layer simulator for sidelink and some of the improved performance by using multiple number of retransmissions as demonstrated in some of the results in that paper. We're going to focus on the acknowledgement-based harq for unicast and groupcast. The basic idea here is we'd like to retransmit a number of times, but once we get an acknowledgement from the intended receiver, then we want to suppress future unnecessary retransmissions. So you can do this for unicast, and the basic model is that I send a transport block and then I wait for an acknowledgements, and if I get the acknowledgements, then I suppress future retransmissions. If I send transport blocks and I never hear from a receiver, there's still going to be some timeout associated with the process so that it doesn't hold on to the resources endlessly. I'll talk about that in a minute. For groupcast, this is when I'm sending from one sender to multiple receivers. There's two modes defined in the standard. There's one's called range-based NAC-only feedback. It's called mode 1 or option 1, and then ACK-NAC feedback, which is mode 2. And this would be the case. So in mode 1 here, a use case would be that there may be a communication range where you want to get some feedback that potentially decoding was unsuccessful. But beyond a particular communication range, you would suppress your NAC feedback. So the idea here would be that within a communications range, you would retransmit and just listen for feedback to those close to you, even though there may be listeners to that groupcast beyond a communications range, and they'll hold their feedback. We're going to talk about the mode where there is no such communication range. So the ACKs or the NACs are sent all the time. So an ACK would be sent, of course, if there's a successful decode. A NAC would be sent if the control channel indicated that transmission was being sent on a separate resource, but then the receiver was not able to successfully decode the actual data packet, even though it knew it was coming. It could then deliver a NAC, which could basically cause the retransmission. Okay. So in order to send this back, we had to introduce the feedback channel. This is called the physical layer PSFCH feedback channel in the standard. There was no need for this in the when we're just supporting blind retransmissions because we didn't have any feedback. Feedback is inserted on a symbol that's periodically inserted in sidelink slots. So either one slot, every other slot, or every 4 sidelink slots. And it's delivered on the next available symbol after a certain time gap has occurred. So there's an example in this paper here, this IEEE communication survey paper, that demonstrates how this works. So this is an example. Let's assume that there's a number of sidelink slots occurring consecutively, and there's data that's sent in this slot. There's a parameter here that basically accounts for processing delay, I believe, that you can deliver feedback in the next available PSFCH symbol after this minimum time gap of PSFCH slots have occurred. So there's basically an assumption that it will take a certain amount of time to decode this particular transmission that occurred in slot N, and that sending on this symbol would be too soon. So with this example where the period is 4, the receiver here will wait until this particular slot to send PSFCH in this symbol. And this value is coordinated between transmitter and receiver so that the original sender knows when to expect that the receiver is going to send it. So basically this gives it enough of a buffer of delay, and then it knows that if I sent in this slot, I should expect in slot N+6 that I should be getting harq feedback from this particular recipient. Now, in practice, there's possibly a lot of different receivers on different subchannels and slots that needs to basically communicate this feedback. And there's a very complicated encoding process. And this tutorial paper goes into some detail showing how every particular slot and subchannel can basically be mapped into some kind of code word that exists on this single symbol of PSFCH feedback. And so this is a rather complicated process. And then this is encoded differently than the rest of all of this. So to fully support this in NS3, we would need a dedicated error model that was tuned to the particular way that this works. So we need to run some link simulations. We're not aware of any support in link simulators for PSFCH right now. So for the time being, we're abstracting this and assuming an idealized perfect feedback channel. So we don't worry about how these are mapped and the coordination here. We just assume that if this traffic channel is supposed to send feedback, we send feedback at this time and it's always delivered to the sender. There's a possibility of contention on this channel. Contention can occur if there's multiple transmissions to make in this PSFCH symbol, or it might want to transmit and receive on the same symbol. So it may have received some traffic and want to send feedback, but it also may have sent traffic and want to listen for feedback. So in practice, the way that the algorithm is designed, you could have a case where a UE had contention locally, not knowing whether to transmit or to receive when that symbol shows up in the slot. And basically this can be worked out with some prioritization, but we're not also modeling this. We're not modeling collisions or contentions right now in the model. Again, we assume a perfect channel and that it could actually, it's a full duplex channel, so it can send and receive in the same channel in the current model. The harq is a stop and wait protocol using what's called a process ID, and there's a small number of these. For uplink and downlink, I think you can have up to like 16 process IDs. For sidelink, the spec says that it's limited to 4 process IDs. And each process ID is corresponding to a transport block. So an example I showed earlier, you have this PDU to send from the RLC layer. It is mapped 1-to-1 for the transmission. The grant is mapped to a process ID. And a MAC instance has a maximum of 4 processes. So while it's trying to get an ACK for this one, it can only send 3 other transport blocks until it basically has to wait for one of these process IDs to clear. So these process IDs can then be reused if the transport block is ACKed or else if it times out. As I mentioned, the logical channel may be configured between 1 and 32 transmissions per transport block. By default, in NS3, we assume 5. There's no way that I could find in the standard to configure blind retransmissions, to note that in the MIB or any of the configuration structures. The way that I chose to implement it is to enable it in the sidelink info that I introduced earlier and set the PSFCH period to 0. So basically it's saying there's kind of like harq with no feedback, blind retransmissions. And the blind retransmissions are selected at random. So as an example that I showed from Samantha's example earlier, it basically grabbed 5 resources, sent the initial transmission, and then grabbed 4 other slots and subchannels at random and sent retransmissions in there. But no feedback is returned. With harq, when we're waiting for ACKs, this has some implications on scheduling. The spec says that the retransmission slots must be selected such that there's an opportunity for feedback to be returned before you retransmit. And this aspect we have implemented in the scheduler. And there's actually a method, if you want to see, there's a method, is min time gap satisfied? And basically in this example, let's assume that UEA is scheduling. And according to the way that harq works, it can determine that UEA should be able to return its feedback in this slot. If that's the case, it would be wasteful potentially to schedule retransmissions in these slots because maybe the first one succeeded. So what happens is that the scheduler, when it picks slots, it makes sure that there's enough time for this cycle of sending and ACKing to have occurred before it schedules another slot. So what we see in the scheduler now is that these retransmissions are spaced, and you may not be able, well, certainly with a packet delay budget of like 20 milliseconds, you're not going to be able to schedule lots and lots of retransmissions and still respect this, this boundary. So this could limit the number of retransmission slots that could be used. But we are, I believe, implementing this aspect of it faithfully according to the standard. So the typical sequence of events are, let's review again, and I've overlaid in red text here some enhancements to what I showed you earlier. So again, in this simulator, the slot boundary occurs, a trigger request is sent. The trigger request tells the scheduler, here's the available harq IDs, because if there are no harq IDs, then there's no point of scheduling something because the MAC is potentially not going to be able to make that transmission. So early in the scheduling process, if there's no available harq IDs at the moment, the scheduler will decline to schedule in that slot. If there are available harq IDs, it will then, well, if they're not harq IDs, it will still publish grants that may have been already assigned harq IDs, but it's going to not create any new grants. That's what this red text is saying. And then the overall process continues like I described earlier, but the only difference is that when I schedule the grants, the scheduler claims one of these harq IDs for a grant in its retransmissions. So let's say 0 through 3 were available. It will pick one of those. It'll pick harq process ID 0. And then it will inform later the UE MAC that here's a grant and here's the process ID for it. When the MAC itself, remember, it dequeues and stores this message from the RLC. It's assigned to a process ID. So the harq buffer keeps track of the process ID associated with that packet. And when it comes time to send, it starts a timer to free this process ID in case there's no response. And I'm not sure whether there's guidance in the standard about this, but I'm setting by default the timer to be twice the packet delay budget. And what happens then is that in case of a positive ACK, it will cancel future retransmissions and the timer and free this process ID. And then the NRUE MAC will start to advertise that this process ID is available again for future grant scheduling. So there's another example program that you can play with to exercise the different modes of operation for sidelink harq. So the purpose of this program is to be able to toggle between groupcast, mode 2, unicast, and broadcast being the blind retransmission in a small network. So I created a 3-node network. When there's unicast is configured, only 2 of these nodes participate. When there's groupcast, one of the nodes is, or broadcast, one sends to the other 2. There's a single flow, and the simulation runs for a configured number of transmit packets. By default, it'll send 100 packets, but you can change that. The output of this program by default is a summary output, which you'll see if you run this program, it'll show by default, it sent groupcast 100 packets. There were 200 packet receptions because we have 2 receivers. And then it prints out some statistics. This packet interreception this is a metric that's defined in the standards. So this program keeps track of that. And then also the minimum maximum delay spread that's observed in the simulation. In addition to this summary, I've instrumented this program to hook some traces in the model and print out explicitly what happens. So let's walk through what happens here in this first example. At this first timestamp, on node 0, which is the sender, I allocate the process ID. It's sending to this groupcast ID. I set the timeout to be 40 milliseconds. Offhand, I'm forgetting what this available is printing out. But anyways, this is the key data here. And then these 2 nodes send back their ACKs at this timestamp. And then at this timestamp, node 0 receives the harq feedback and it deallocates the process ID and makes it available again. It then will receive another ACK, but basically it doesn't act on this because it's already deallocated it. So we had a choice in our model. When you have group cast harq, do you consider that everything's act when everybody's returned an ACK to you, or when some subset of the receivers has returned an ACK? So the way it's implemented now is that it only looks for a single ACK from somebody, and then it'll cancel the retransmissions. But a different policy could be implemented as well, like waiting for all before I basically give up any retransmission. So then, if any, the scheduler then should not be resending any retransmissions until this time interval between this timestamp and this timestamp has taken place. But the scheduler then is free to schedule retransmissions of this that could occur after this time. So you can actually see in the logs, again, this log command, or this NS3 command, dumping into a log file. If you look into the logs on these specific lines, you can see the simulation events corresponding to what I showed you on the previous slide. This is where the grant has been created from the scheduler. It's telling the Mac about it. It's saying, here's a new grant for you. It's going to use this harq process ID. The Mac needs to know it at this point in time, because it's going to ask the RLC to give it a packet. And then that packet, when it comes down, has to be stuck in this harq buffer and associated with a particular process ID. There's a different object that manages this. The NRSLUE Mac harq object is basically the harq buffer. And you can see that log output here. There's a trace that you can hook, which is actually responsible for those prints that I showed you earlier. That's called, and then it also logs that it's assigned this process ID when it makes this first transmission. And then a positive ACK causes the harq buffer to be flushed. So that transport block is removed, and then this harq ID becomes available for future use. Any questions about harq and the harq support?
Real briefly, I believe that the available print was the number of available harq process IDs based on the rest of them.
It probably is. So. Okay. Well, if no other questions, I'll just wrap up. Again, the overall message of this tutorial is that look for some changes upcoming in CTTC's V2X branches with these extensions for multiple subchannel sensing, dynamic granting, support for multiple logical channels in the scheduler, and then unicast and groupcast harq. The focus here has been to have a high amount of fidelity in tracking of the standards at the MAC layer. There are some abstractions at the physical layer, like our perfect PSFCH channel. The traffic channels and the control channels are not perfect. They use an error model, but presently, until we get some link simulations done or put some kind of a surrogate model in there, there's a perfect feedback channel assumed for this model. But the purpose of doing this is that more accurate sensing and scheduling model, as well as harq, should support more accurate latency calculations by the simulator, which we presume is what people are going to be interested in when simulating a sidelink within S3. We are going to upstream all of this work to CTTC's public branches in the next month or two. Again, the limiting things is to transcribe this tutorial content into the documentation that'll be published, and to do some additional tests. Once that's done, we can go ahead and move towards merging it there. If you're interested in tracking this work in the future, keep an eye on the merge request link that I've included there. There's also a user mailing list. So if you have technical questions, we prefer that we just put them on the Google Groups forum for 5G Lena. And that's all I have. Any questions before we move on to the next tutorial?